Welcome students, welcome to Priya's Life Science Academy. This is your educator Priya. I was teaching you population ecology. Now let's continue with the chapter. First I'll complete the ecology part, then I'll start evolution. Okay. So today we are dealing with a very important point, which is what is Iteroparity and what is Semelparity. These two are reproductive strategies. Okay. And then after that we will go to the population growth curves. There are two types of population growth curves which we will study. So first let's understand what is Iteroparity, and this lecture will be beneficial for those who are in B.Sc, in master's degree, or those who are preparing for CSIR, NEET, Life Science, UPSC, NEET, etc. Okay. So let's understand what is Iteroparity. Iteroparity is a reproductive strategy in which an organism reproduces multiple times over its lifespan. A type of reproductive strategy where an organism have a chance to reproduce multiple times over its lifespan. Like us, we humans, we have multiple chances to reproduce in our lifespan. These species typically invest long-term survival, parental care, and multiple reproductive events to increase their chances of passing on genes. Okay, so we invest parental care, we invest in long-term survival, okay, and we do have multiple reproductive events. So humans, Homo sapiens, we can reproduce multiple times throughout the life. Elephants also, Elephas maximus, give birth to several offspring over their lifespan. Then oak trees, okay, produce acorn seeds annually. Dogs, cats, birds, they also reproduce annually. Many animals reproduce multiple times over its lifespan. For dogs and cats, they have a specific season in every year, okay, so they can reproduce multiple times over their lifespan. Okay, so this is one type of strategy where you have the chance to reproduce multiple times over your lifespan. Now, in contrast to Iteroparity, there is another reproductive strategy which is known as Semelparity. Okay, Semelparity is just opposite. It's a reproductive strategy in which an organism reproduces only once, okay, only once in its lifetime, typically investing all its energy into a single large reproductive effort before dying. So they will only have one reproductive event in their lifespan, and they will give their total energy into that reproductive event. Example, Pacific salmon, okay, spawns once and then they die. Bamboo tree, some species flower and seed only once in decades before dying. We know that there are some trees which only give fruits one time in their lifespan. That is a strategy known as Semelparity. Okay, grows for years, flowers once and then dies. Some insects like mayflies lay eggs once and then they die shortly after. So these reproductive strategies are applicable for both animal and plants. In animal and plants, we can see these two types of reproductive strategy. One is that I have multiple chances for reproduction like us and many higher animals like dogs, cats, okay. And there is another strategy which is Semelparity, where you have one single chance for reproduction and you produce a large colony. Like you have seen flies, they produce only once in their lifespan and they produce a large colony. So just opposite, we have chance for multiple reproduction and we produce a single offspring, or in case double offspring, okay. But in Semelparity, you have only one chance, and in one chance you are given chance to produce a large colony, okay. So that's the difference between Iteroparity and Semelparity. Now the difference is here. So productive events for Iteroparity is multiple times over the lifespan, and for Semelparity only once. And as we have parental investment, often high care for offspring, and for Semelparity it's low or none. Okay, and lifespan usually long for us, usually long lifespan, and Semelparity usually short lifespan, and energy allocation spread over lifespan, like our energy is divided in many physiological work, and we need energy for every reproductive event, so we save our energy for over our lifespan, and that is spread over the lifespan. But in case of Semelparity, all at once into reproduction. Their main goal is to reproduce a large colony, and in that they give a lot of energy. Okay, so I hope you understood, and from this I hope you remember the survivorship curve I told you. So for this type of animals which are going through Semelparity, they are in type 3 curve, because a lot of offspring are produced and not all the offspring are healthy to survive. Once some of them are healthy to survive, they then have a growth curve. And for this Iteroparity, it is the type 1 curve. Like for us humans, we have only a single reproductive event, and as we get parental care, our chances of survival in the young is very high, then it's low due to illness, etc. So that fits into type 1 curve. So these are all included in population ecology. Now the important point which I want you to understand, that is population growth curves. So you know that a population, and I hope you understood what is population and you remember what is population, like a group of organisms where the individuals of a same species stays. Okay, so that is known as a population. Now what is population growth curve? Population growth, refers to the change in the number of individuals in a population over time. So for example, there are 10 individuals of a population today, and after 10 days or after 10 years, how many organisms are leaving, okay, or how many organisms are died. So that actually refers to the population growth curve. Scientists have discovered the formulas to estimate the population growth beforehand, and they also gave us two curves. So the size of a population of any species is not a static parameter. You know that population keeps changing with time, and there are a lot of factors upon which the population growth depends. That is food availability, predation, atmospheric pressure, adverse weather. So environmental factors plays a major role in shaping population growth. So there are two types of population growth curves. One is exponential growth and one is logistic growth. This is exponential growth, also known as a J-shaped curve, because this growth gives us a pattern of a J-shaped curve. And another is logistic growth, which gives us a pattern of S-shaped curve. Okay. Now, exponential growth curve, which is J-shaped curve. In this type of growth form, the population grows exponentially. What do you mean by exponentially? Exponentially means in a very large quantity, unlimited growth. And why this happens? This happens because of the unlimited availability of the resource. There is an unlimited availability of the resource. Lots of resources are present. That's why organisms are eating and they are getting the chance to survive and they are getting the chance of growth. So lots of organisms, growth is very higher in case of exponential growth. So in this type of growth form, the population grows exponentially. I told you what exponentially means, and after attaining the peak value, population may abruptly crash. Of course, when resource is finished, the population will also abrupt. This increase in population is continued till large amount of food materials exist in the habitat. Of course, till the time there is a lot of resource, the population will tend to increase in number. After some time, due to increase in population size, the food supply in the habitat becomes limited, which ultimately results in decrease in population size. It's very simple. When a lot of amount of food is available, the population is growing smoothly. When population is growing, and when it is consuming a lot of food, now there is food scarcity, and when there is food scarcity, there will be no population growth. Okay, now you can see the figure, J-shaped growth curve. Like at first the population grows abruptly, the population is growing, and at the point when resource is scarce, there is no population growth. Okay, so this is the number of the individual and this is the time. So upon time, the number of individual is growing exponentially because there is a lot of available resource. Okay, lot of available resource. For example, many insect populations show explosive increase in numbers during the rainy season. Have you noticed that during rainy season there is a kind of fly which increases in number? Or you can say that during autumn there is a kind of fly which also increases. We can only see the fly in that season. Why? Followed by their disappearance at the end of the season, because of the environment supports their growth, because of the food availability, so they get the food available on that particular season. That's why they are getting the chance to grow, and at once the resource is finished, the population just crashed. Now the following equation exhibits J-shaped growth. So there is an equation of this growth which is dn dt equal to Rn. What do you mean by dn dt? dn dt signifies the rate of change. Okay, you know that's a formula of calculus. dn dt means dn dt always represents any kind of change, the change in time, okay, of the population. Now what is R? R is biotic potential, or R can also be designated by per capita growth rate or intrinsic rate of increase. I am coming to this later. And capital N is the population size. You know, before R was denoted as B minus D. B means birth rate and D means death rate. So it is birth rate minus death rate. But scientists wanted to make it very simple, so they denoted B minus D as R, small r. So this small r is very important, which represents the per capita growth rate or intrinsic rate of increase. Okay, I hope you remember what is capital R. Capital R was net productive rate, and this small r is the intrinsic rate of increase. There's a relation between capital R and small r. We will deal with this in the next video. Okay, so for now, you have to understand the small r. The small r is very important for this exponential growth and logistic growth. This is the intrinsic rate of increase, or you can say biotic potential or per capita growth rate. Okay. Now, how B and D can be taken out? You know that often the number of births and deaths are expressed per individual in the population. So, the birth of 100 cockroaches to a population of 1000 would represent a birth B is equal to, so if 100 cockroaches are born of the population, total population 1000, then the birth rate will be 100 by 1000 is equal to 0.10. Okay, so this is how the birth rate is taken out. Now similarly, so 0.10 per individual per week. Okay, similarly the death of 50 cockroaches in a population of 1000 would be a death rate D of 50 by 1000 or 0.05 per individual per week. So now we can rewrite the equation giving the rate of change in the population. So delta n by delta t is equal to Bn minus Dn. So we can write it simply by replacing delta n delta t, which is dn dt, which means the same. Dn dt is equal to B minus D. And here is n. This n is taken as common. Simple mathematics. So the formula, the ultimate formula is dn dt is equal to Rn, because now B minus D is referred as R for simplicity. Okay. B minus D is birth rate minus death rate, which denotes as small r, which is biotic potential or intrinsic rate of increase or per capita growth rate into capital N, which is the number of individuals or population size. Okay, so I hope you understood the formula. What is dn dt? So dn dt means change in the number of individuals in the population. So how the population is changing, we can denote it as dNdt is equal to Rn. R is the biotic potential, or the intrinsic rate of increase multiplied by capital N. Okay. Now dNdt equal to Rn, we can also rewrite this equation to find sizes at various times. Okay. The population size at time t is given by nt equal to n0 e to the power rt. So that dNdt is equal to Rn formula can be written like as this to get the population size at various times, where n0 is equal to the population size now at time 0. E is the base of natural logarithms, a constant of about 2.70. Okay, and R is the per capita growth rate I told you, and small t is the number of time intervals. So if we do a sum with this formula, we can say that where n0 equal to 10, the initial population size is 10, t equal to 2 years or 2 weeks, it can be any, just an arbitrary example. R equal to 0.1, R is the per capita rate of increase. So after 2 years, the what will be the population growth? So nt plus 2 is equal to n0 e to the power rt. The following the same formula, n0 is 10, e to the power rt, r is 0.1 into t. So you got the result. So it's very simple. So exponential growth rate has two formulas. One is dNdt equal to Rn, the simple formula, and the formula can be written as this when you have to include various time. Okay, and one last thing for this exponential growth is R decreases as generation time increases. Okay, R decrease means R is the per capita growth rate. So the per capita growth rate or intrinsic rate of increase decreases as generation time increase, because unlike us, for humans, for elephants, our generation time is so long. For human it takes 9 months. So generation time is increasing. As generation time increases, R decreases, the per capita growth rate decreases. But in case of small animals or flies, you can see that the generation time is very less. That's why they produce a large number of progeny. Okay, so their R also is a high according to them. So for a brush up, what is exponential growth? Like, exponential growth happens when there is unlimited resource available and the population grows in unlimited way, and when the resource is limited, the population growth stops. And this is denoted by a graph which is a J-shaped growth curve, and it is denoted by a formula also, dNdt equal to Rn, by which you can understand the population change over time. Okay, now likewise capital R, I told you about the net reproductive rate. The small r also denotes something. When small r is equal to 0, the population remains constant. Very true, because when the intrinsic rate of increase is 0, then the population will not grow. When r is greater than 0, the population increases. Of course, when the intrinsic rate of increase is greater, then the population will also increase. When r is less than 0, the population decreases. When intrinsic rate of increase is decreased, the population will definitely decrease. Okay, so this is important. For example, like in the Newfoundland beaver population, I gave you the sums where r is equal to minus 0.0162. That means the population is declining. Where the intrinsic rate of increase r is low, there is no population growth. Okay. So the sum up, graphical representation is the J-shaped curve. The curve starts slowly and then grows steeply upwards, indicating rapid population growth. Okay, now exponential, the important point about exponential growth occurs in ideal conditions with unlimited resources, no limiting factors like food shortages, competition or predation. There is no limiting resource, no limiting factors. Growth rate remains constant but population size increases rapidly. I told you population size increases rapidly like a J-shaped curve. Common in bacteria, invasive species and species in new habitats. Okay, and exponential growth is not sustainable because resources eventually become limited. This will only happen in an ideal situation, and an ideal situation is not practical situation. There is no ideal condition in the world where resource is unlimited, so it's not sustainable growth. Okay, Now coming to the logistic growth, which is more realistic. Exponential growth is somewhat when ideal condition is there, it's somewhat very superficial, but that's not realistic. But logistic growth is very realistic. It's the shape of the curve is S-shaped. The sigmoid growth curve is also known as the logistics growth curve, which is S-shaped. When few organisms are introduced in an area, the population increase is very slow. In the beginning, that is the positive acceleration phase or lag phase. Suppose, for example, when few organisms are brought in an area where there is medium amount of resource, the organisms tend to grow very slowly. That's known as the lag phase. Like they are accelerating slowly. In the middle phase, the population increase becomes very rapid, which is known as the logarithmic phase. Okay, so in the middle, they will eat and they will eventually grow. So in the middle, the phase is logarithmic, their growth is rapid. And finally, in the last phase, the population increase is slowed down, that is negative acceleration phase. Because same, the resource will all be used up and there will be no resource available for use by the population, so the population will decline. So at first the population is growing. I'm showing you the curve, you know, here. At first the population is growing, the lag phase. Slowly it's increasing, and after that the rate also slows down. Okay, and it declines. This is the S-shaped curve for logarithmic growth curve. Okay, I'll come to this later. The level beyond which no major increase can occur is referred to as the saturation level or the carrying capacity, which is denoted by K. Okay, there is a carrying capacity. Now, what is carrying capacity? Carrying capacity is denoted by capital K, which is like, for example, you are invited to a marriage party, and the owner of the party has organized marriage ceremony for 1,000 people. So his carrying capacity is 1,000 people. He can only afford food for 1,000 people. Okay, but eventually what he saw that without invitation some people are coming in, and the population has increased into 1,000, 100, 500. So the carrying capacity was 1,000, but if more people are invading into the situation, what will happen? They will get no food because carrying capacity is limited. That is known as carrying capacity. So the amount of food available to support the organisms in the population, so the total amount of food available to support the organisms in the population is known as the carrying capacity. Okay, in the last phase, because so when the population attains the carrying capacity, then the population will eventually decline because no more food is available to support the organisms. In the last phase, the new organisms are almost equal to the number of dying individuals, and thus there is no more increase in the population. The J-shaped sigmoid growth form is represented by the following equation. Now, here is also the equation of the logistic growth curve, which is T n dt equal to Rn k minus n by k. Now, let's understand the formula very nicely. I told you that whenever you see the T n dt, it denotes any kind of change. So, change over time. Okay. N is the population size, T is the time. So, it's the rate of change in population size over time. Understood? Now, what is R? R, I told you, R is intrinsic rate of increase or per capita growth rate or biotic potential. What is N? You know, N is the population size. Okay. Now, what is K minus N by K? I told you that K is the total carrying capacity. Okay, and N is the population size. So when some of the organisms have used the food of the carrying capacity, use the resource, so how much food will be left? So K minus N divided by K. It's a ratio. It's the proportion of unused resources remaining. Okay, for example, that I gave you, 1,000 was the total carrying capacity, and 500 people only came in for the first batch. So how much left? 500. So now if I want to take out the proportion, so K minus N, which is 500 divided by K, divided by K, which is 1,000. So half Half amount of food is left. It's very easy to understand. 500 into 2 is 1000. Okay, so this is the way you have to understand. So K minus N by K is the proportion of unused material left in the population. Okay, I hope you understood the equation. Now let's understand the graph. This is the time on the x-axis, and the population size or the number of individuals is in the y-axis. So you can see the rate is actually increasing, and this is the point of maximum growth. I am coming to this later. Now after it is becoming the peak, and then the rate slows down when reaching the carrying capacity. So you know, this blue dot, it is the carrying capacity of the environment. So environment can only support this much individual. Environment can only support food for this much individual. When the carrying capacity is reached, then there will be no food available to support the organism, so the population growth will be slowed down. This is the logistic or restricted growth form, and this is the more realistic growth form in the environment. So I have food for 1000 individuals. So 1000 individuals are attained. No, if any individuals are coming in, there will be no growth, because only that much food was available. So logistic population growth will occur when population numbers begin to approach a finite carrying capacity. Okay, the carrying capacity is the maximum number of species that can be sustainably supported by the environment. I told you, as the population approaches the carrying capacity, environmental resistance occurs, slowing the rate of the growth. You know that when the growth approaching the carrying capacity, its growth is slowed down. This results in a sigmoid S-shaped growth curve that plateaus in the carrying capacity, denoted by K. You can see the curve declines. Logistic growth will eventually be seen in any stable population occupying fixed geographic space. Okay, it's a more realistic form you can see in any kind of environment where there is a stable population. The carrying capacity of a biological species in an environment. Now, what is carrying capacity, which is denoted by K? The carrying capacity of a biological species in an environment is the maximum population size of the species that the environment can sustain indefinitely, giving the food, habitat, water and other necessities. So what do we require for living? We need a good environment, we need a good food, we need water, we need the good habitat. So that's total is known as carrying capacity. So the total capacity of the environment which can support the organisms in a population, that is known as the carrying capacity. In population ecology, the carrying capacity is defined as environment's maximum load. So how much organisms can be supported by that available resource, that's the environmental maximum load. Carrying capacity was originally used to determine the number of animals that could graze on a segment of land without destroying it. Later the idea has been expanded to more complex populations. So carrying capacity is very much beneficial for farmers. You know that you have a land, so you want to graze your domestic animals on the land, and you know the carrying capacity of the land, so you can decide, okay, how much cow I will allow to graze on the land so that my property will not be destroyed. So if you know the carrying capacity, that how much the environment can support the cows, then you can understand that how many cows you will put on the ground. You will put on the ground for grazing. Okay, that's very important. If you brought the cows that exceeds beyond your carrying capacity, then your land will be destroyed in a day. Okay, I will give you one very important example, which is MSY, or maximum sustainable yield. What is it? Like I want you to show, like, you know, this point in logistic growth, this point is known as maximum growth. Why this point is known as maximum growth? Let's see. In logistic growth, the maximum population growth rate occurs when the population size n is half the carrying capacity. Here you can see in the graph only that your carrying capacity is this much. Okay, and when you attain the half of your carrying capacity at this point, you can see the growth is maximum. You can see the graph is low, and the graph is the highest here at this point. So when your population size is half of the carrying capacity, so when your n is k divided by 2, then you got the maximum yield. the maximum growth of the population. Okay, so that's known as maximum sustainable yield. So MSY, or maximum sustainable yield, is the largest yield harvest that can be sustainably extracted from a population without depleting it over time. And this method is useful for lots of farmers, lots of fishermen. Okay, it occurs at the inflection point of the logistic growth curve where n is equal to k by 2. When you have the number of individuals which is half of your carrying capacity, then your growth is maximum. Okay, at this point the population grows at maximum rate, meaning it can replenish itself more efficiently after harvesting. Okay, so fisheries, forestry, wildlife management, they ensure sustainable resource use by using this method. They harvest when there is a nk by 2, because when you have this point, okay, when you have this point and when you harvest at this point, there will be then enough individuals of the population left to attain the growth. Okay, so at this point the growth is maximum, and again this is used in case of fisheries, in case of forestry. So if you pick up and if you harvest your cereals, or if you harvest your fish at this point, what will happen? There will be enough individuals left to attain the growth, because at this point their growth is maximum, so they can replenish themselves very easily from this point. Okay, so let's see this with a mathematical example. If your carrying capacity is 1000, I have 3 situations to get you notified about this point, like when your n is at higher, when your n is at medium, when your population size is very high. So let's understand this by a very simple mathematical example. Here I have 3 examples you to give. So here your n is much less than carrying capacity. Here your n is equal to, here your n is half of the carrying capacity, and here your n is much higher than the carrying capacity. That means what? Like here the individuals are much lower than the carrying capacity, here the individuals are half of the carrying capacity, and here the individuals are much higher than the carrying capacity. In 3 of the case, this formula applies, d and dt equal to Rnk minus n by k. So we wanted to understand by a mathematical problem where we apply this formula, this logistic formula, and our intrinsic rate is same, that 0.1, 0.1 and 0.1, and the carrying capacity is 1000 for 3 of the sums. Only the difference is the population size. Here the population size is very low, 100. Okay, here the population size is medium of the carrying capacity, that is half of the carrying capacity. So our carrying capacity is 1000, and what is the half of the 1000, which is 500, and here is the carrying capacity is much higher, if it is 1000, the carrying capacity is 900, so only 100 left, so only 100 lower than the carrying capacity. So very much high population size here. Here the population size is half of the carrying capacity, and here the population size is very low. In 3 of the case, what you can see that here the population growth is 9, here 25, and here 9. What did you get from this? That whenever your population size is half of the carrying capacity, then the population growth is maximum. So that is why at this point we get maximum sustainable yield. Okay, so always remember that whenever your population size is half of the carrying capacity, then your population grows at maximum. Okay. Now the key points of logistic growth phase. First is initial lag phase. You know that slow population growth due to adaptation. At first, when a population is introduced, their growth is slow. Exponential growth phase. Then again, then after that, they just tries to increase their size when resources are abundant. Then again, when reaching the carrying capacity, growth slows and also resources become limited. Carrying capacity, the maximum population size and environment can sustain. Stable equilibrium phase, population size stabilizes around the carrying capacity due to resource limitations and environmental resistance. Okay. Density dependent factors, factors like food availability, competition, disease and predation regulate population size. Sustainable growth, yes, unlike exponential growth, logistic growth is more realistic in nature as it considers environmental constraints. Okay, in exponential growth there is no environmental constraint, that resources are unlimited, but here resources are limited, and that's a true condition of any kind of environment. Logistic growth stabilizes as resources become limited, reaching the environmental carrying capacity. You know that the growth stabilizes itself when it reach carrying capacity upon limiting resource. So when resource is limited, it attains the carrying capacity and its growth is limited. So I hope you understand, students, these two growth curves. So exponential growth is not realistic. It's for ideal condition, and there's no ideal condition prevails in the nature where resources are unlimited. But logistic growth is more realistic where there is environmental constraints. I hope you understood. If you have any questions, you can comment below. I'll be happy to give you a suitable reply. As I always say, fight for your dreams will fight for you. Thank you, students.